A second important and fundamental concept is the concept of asymptotics, namely what happens to an estimator or a test statistic as the sample grows to infinity. And the idea of asymptotics is to actually do away with some of the very strict assumptions that are required to get results in finite samples. The classical approach for finite sample properties is to assume a lot. For example, to assume a normal distribution, or to assume all kinds of things being fixed, like independent observations, fixed variances, and so on. So to relax this and to allow some more complexity in the models, one needs to get the information from the size of the data set. So that's really the idea why we use asymptotics. We gain information about the underlying parameters in the model as the sample grows. Now, of course, this only works if, in fact, as the sample grows, we do have more information. And for example, if as the sample grows, everything changes all the time, then this doesn't work. So the key concept in here is that of smooth change, of continuity. And as long as things all change in the same direction and move towards a given point, then we can exploit the asymptotics to derive properties that hold in the limit, and then through some transformation that we'll see in a few minutes, we do something which is actually a little bit counterintuitive, especially the first time around, is we get something which looks like finite sample properties, but they're really based on properties in the limit. So first, in order to move towards asymptotics, we need what is called regularity conditions. And these are the collection of assumptions that we need in order to get this smooth transition, this continuity. And they basically boil down to constraints on the degree of variability that we allow as the sample moves to infinity. Ideally, we don't allow any variability, but that is not very realistic. That's typically the classical assumption of independent and identically distributed random variables. But in a lot of what we will work with, the random variables, the error terms, for example, will not be identically distributed. They will be heteroscedastic, say. They will not have a constant variance. And they may also be correlated. So how do we deal with that? We deal with that by putting constraints on these moments. For example, in terms of the variance, we exclude extreme values by saying the variance cannot be infinite. In other words, observations cannot be infinitely large or infinitely large on the positive scale or on the negative scale. So the values that we observe have to be reasonable. In other words, they can't be jumping all over the place in crazy ways. So the variance is somehow constrained. The variability is constrained. In a spatial domain, we also need that these moments are regular across space, because we'll move to the limit across space, so things can't be changing. In fact, this is the notion of stationarity creeping back in. We can't have it that as we expand, for example, the spatial domain, that all of a sudden the properties of a function or of an estimator become different. They have to be the same. And one way to deal with this is to, in terms of spatial autocorrelation, is to enforce distance decay. If you enforce distance decay, then the degree of spatial correlation decreases as the distance that separates two observations increases. In other words, there is a point beyond which two pairs of observations are, for all practical purposes, no longer correlated. And so if you have enough of these, you can think of it that way, as you go to the limit, you get more and more and more of these seemingly uncorrelated observations, so then you can extract that information as if you had a sample of uncorrelated random variables. Of course, that is much smaller than the one that you start with. So that's the rationale of these asymptotic conditions, and they're very formal mathematically. They're very complex, but an easy way to get an intuition for them is that first of all, you cannot get crazy heterogeneity, so you have to somehow constrain the degree of variability. And secondly, you cannot have that everything is correlated with everything else equally strongly. So you need some kind of distance decay in the spatial dependence, which ensures effectively that there's a range on the spatial dependence beyond which there is no longer any spatial dependence. The two building concepts that we use to work with asymptotics are what happens in the limit, and what happens in the limit in two important respects. First of all, what do this statistic or this estimator, what does it move towards? And this is encompassed in what we call the law of large numbers, or LLN. And the law of large numbers has to do with what averages of the sample, and in a very general way, as we'll see in a few minutes, what an average of the sample moves towards. And ideally, we want that average to move towards the true value of the parameter, the true mean, or the expected value. So that is called consistency. If in the limit, the estimator reaches the true value of the parameter. So to establish consistency, we will typically form some kind of average from the data, or a function of the data, which of course includes the parameters, and have to establish that that average goes to the correct true underlying parameter value. So that's the law of large numbers. Law of large numbers has to do with consistency. And then the central limit theorems, CLTs, have to do with the distribution of this parameter, because ultimately we want to do something that's the equivalent of a t-test, and we will call it an asymptotic t-test. We've already covered this when we talked about specification testing. So, but here's where there's a kind of an intellectual trap, because in the limit, the estimator, if it is consistent, in fact becomes a constant, because it converges towards the true underlying parameter value. And that parameter value in classical statistics is a constant. It's not a random variable, it's a number. If the true parameter value is 5, then in the limit, if you have a consistent estimator, that estimator equals 5, and not 5 plus or minus anything, just 5. So that doesn't work for us to do significance tests in the traditional sense. So a central limit theorem really quantifies how the estimator moves towards the limit in terms of its randomness around the true end value, around the true parameter value. So as the sample grows, we get more and more information, and presumably the estimator gets closer and closer to the true parameter value, but closer and closer in a random sense. So that means it still moves around, and hopefully it moves around the true mean, the true parameter value, but its variance in some sense becomes smaller and smaller as we get more and more information. And the central limit theorem quantifies the way in which this happens by proving that some transformation of some standardized random variable, typically, subtracting the true mean value and standardizing by some measure of variance or square root of the variance. This entity, which is a random variable, follows a normal distribution, and that is then called asymptotic normality. Now, it's a little bit counterintuitive because asymptotically, in the limit, there is no normality whatsoever. In the limit, the estimator is a constant, so it has no distribution. So this is really about what is the randomness of that estimator around the true parameter value as we move towards the limit, and that is captured in a central limit theorem. And now we'll look a little closer at what each of these means in our spatial context. So first of all, in full generality, what we need is something that is called a uniform law of large numbers. And it's all about consistency, but it's not consistency necessarily of an estimator, but it's very general. It's consistency of any function computed from the data, which of course includes the parameter value. So in general, a uniform law of large numbers establishes that the average, on average, as n grows, the average difference between the true function value and its expected value, its mean, in other words, becomes negligible, goes to zero. In other words, in the limit, this function from the data equals its expected value. And that's what the law of large numbers is about. And this sounds a little abstract, but it's really an incredibly powerful concept because it allows us to do this for any number of functions of the data, including, for example, the maximum of a likelihood function. So we can establish that the maximum likelihood estimator is actually consistent in a particular context. So that's where this law of large numbers comes from. So the easy way to get an intuition from this is to think about, the average of some function of the data, that this average, as the sample contains more and more information, moves towards the limit, this average actually converges towards its theoretical expected value, which is what we would like. And then the second concept, the central limit theorem, is about the difference between the estimator and its true underlying parameter value. And as we gain more information in the sample, of course, in the limit, we just talked about this, in the limit, this estimator will equal the parameter value, so there will actually be no randomness left whatsoever. But as long as we rescale the difference between the true value and the estimator by the square root of the sample, so this actually blows up, if you think of it, the difference between the two. So you can think of this as two countervailing forces. One is the difference between the true parameter and its estimator, the beta minus b, and that becomes smaller and smaller and smaller as the sample size grows. And then if we multiply this by the square root of n, the sample size, that square root becomes larger and larger as the sample size grows. So the product of the two, the central limit theorem, establishes that the product of these two forces, one becoming larger, the other one becoming smaller, follows a normal distribution, a Gaussian distribution with a zero mean, which means that on average the estimator equals the true population value, but also with a covariance matrix if it's multivariate. And now the tricky part will be to establish what that variance covariance is, and that's specific to each situation. And the way we do this technically, if you're interested in some of the mathematical detail, is we establish a Taylor expansion around a true value and then establish what happens to the different parts as we move to the limit and use various properties to establish that this actually follows a normal distribution. So this is way too technical for the treatment here, but it gives you kind of an idea what the central limit theorem is about. And then, of course, it lets you treat this rescaled variable as if it is a standard or a regular normal random variate. And typically what we'll do is write this, work this out, and so say that the distribution of the estimator B will follow a normal distribution after being rescaled by 1 over n, which so we divide it by the square root of n, then the mean will be beta and the variance will be 1 over n times v. Because it's the variance, we take the square of the square root of n. So that's how this works in practice then. So in practice, you often see reference to asymptotic normality. That's really what this is about. It's about how the rescaled difference between the estimator and the true value is random around the true value as we move to a larger and larger sample. And it's important to keep in mind and to recognize the difference between this and the actual asymptotic value of the estimator, which, because of consistency, is the true parameter value, or in other words, it's a constant. It doesn't have a distribution. So that is the sense in which asymptotic normality needs to be understood. It's not normal in the limit, but as it moves to the limit, the variability of the estimator around a true parameter value follows a normal distribution. Okay, then in the spatial context, it's actually not that simple to think about how we move to the limit. So unlike a time series where the limit is the future, infinity far away, in space we have 2 dimensions to deal with. So it is not unambiguous how the sample grows as we go to infinity. How does it grow in the 2 dimensions? And in fact, there are 2 separate types and also combinations of the 2. One is called increasing domain asymptotics, and most of what we will discuss will fall under this category. The other one is called infill asymptotics. And they're very different. And unfortunately, in terms of the math, in terms of the actual properties of different estimators, the 2 are not equivalent. So it is not automatic that something, an estimator, for example, or the consistency of an estimator that is established for increasing domain asymptotics also holds for infill asymptotics. So what are these 2 types then? Increasing domain asymptotics is really a notion of unbounded space. You can think of an infinite range where you start with a small set of observations and you expand them at the edges. You add new observations at the edges. This has 2 consequences. One is, as you add new observations at the outer edges, the neighbor structure, remember we're doing spatial effects and we'll need a weights matrix, the weights matrix actually changes because the neighbor structure at the boundary changes as we grow the sample. This is a non-standard phenomenon. You don't get this in standard asymptotics, so you need to take care of this. You need to deal with this in the formal treatment of the proofs and the derivations. And the technical concept that deals with this is called a triangular array. And we won't get into specifics here, but you might see this term used in papers or in textbooks. And that's really what this is about. It's an additional mathematical complication to deal with the extent of variability as we move to the limit. Remember, we don't want a lot of variability. We want everything to be smooth and continuous and moving to this limit. But as we add new observations, new areas at the edge, we create boundary effects, which is additional variability that we then need to correct for in the formal proofs. The good thing, so that's a bad thing. The good thing about increasing domain asymptotics is that the number of neighbors does not depend on the sample size. You can think of counties. Think of counties in the US. Let me show you the pictures. So let's say this is somewhere in Kansas. We start with the yellow counties and we keep adding counties at the edges. The number of neighbors of the counties is on average 4 or 5 or 6, something like that. But it doesn't really matter whether we have 50 counties or 50,000 counties, the number of neighbors is roughly the same. In other words, the density doesn't really change as we add observations at the outer edge, as we move towards the limit. In contrast, the notion of infill asymptotics is a notion of bounded space. So the previous notion was about expanding the domain of space, moving to infinity. Infill is a sandbox in which we get more and more sample observations. So it's I call it a container view, and we add additional observations in the container. So as we add additional observations, we approach a continuous sample. We approach the best information we can get. That's a good thing. The bad thing in this case is that depending on how we define the neighbors, the number of neighbors can increase with the sample size. For example, if you define neighbors as those observations within a given distance range, then as you put more and more of these observations in the container, there will be more and more of them in the distance range, so the number of neighbors will increase. And the example I have of this is, in this case, the location of housing units as it happens in Orange County, in California. So you can think of the general outline as being the container, and as we drop more and more points in this, we get a denser and denser sampling surface, and this is how we approach the limit, how we approach infinity. And as it gets denser and denser, of course, each given house will have more and more houses within a given radius of itself. So important concepts for asymptotics are the concept of a law of large numbers, which is about establishing the consistency of an estimator, making sure that some kind of average of a function of the data moves to its theoretical expected value, and a central limit theorem, which has to do with establishing the randomness of the difference between the estimator and the true value. We call this asymptotic normality, but we know it's actually not in the limit, it's as we move to the limit. And this asymptotic normality will be the tool that we use to carry out inference, to do significance tests. And then important in the spatial context that we have two ways of thinking about asymptotics. One is called expanding domain, the other one is called infill asymptotics, and there are also hybrid forms that are combinations of the two.